This is a video from section 3.3. We're going to look at problem 33. It says, show that if V is orthogonal to both W sub 1 and W sub 2, then V is orthogonal to K sub 1 W sub 1 plus K sub 2 W sub 2 for all scalars K sub 1 and K sub 2. So we're going to look at the proof. It says, assume V is orthogonal to both vectors W1 and W2. Let K1 and K2 be scalars, okay? Now, we want to show that V is orthogonal to K sub 1 W sub 1 plus K2 W2, right? So in other words, we want to show V is orthogonal to the linear combination of W1 and W2. Since V is orthogonal to W1, then the dot product of V and W1 is 0. Since V is orthogonal to W2, we can say that the dot product of V and W2 is 0. Now what we want to do is we want to look at the dot product of V and the linear combination of vectors W1 and W2. So in other words, we want to look at the dot product of V and K sub 1 W sub 1 plus K sub 2 W sub 2. But we can distribute the V to each vector within the parentheses, right? And so, in other words, we can write this as the dot product of V and K sub 1 W sub 1 plus the dot product of V and K sub 2 W sub 2. But we can pull the K sub 1 out in front. And so we can write this as K sub 1 times the dot product of V and W sub 1 plus K sub 2 times the dot product of V and W sub 2. So I rewrote and reiterated. So the dot product of V and K sub 1 W sub 1 plus the dot product of V and K sub 2 W sub 2 is equal to K sub 1 times V dotted with W sub 1 plus K sub 2 times the dot product of V and W sub 2. But remember that V is orthogonal to W sub 1. And so the dot product is 0. And V is orthogonal to W sub 2. So the dot product of V and W sub 2 is 0. So on the third line, we get K sub 1 times 0 plus K sub 2 times 0. But that's 0 plus 0, which is 0. And so what that tells me is V is orthogonal to K1W1 plus K2W2. And that'll do it for this video for section 3.3, and we worked problem 33. Thank you.